So welcome to lecture 12.2 of the group theory course. In the previous lecture we discussed plane wave solutions at the x point. We are discussing in this chapter the band structure of cubic crystals. In most cases we are discussing the empty lattice approximation and the nearly free electron model, and how group theory helps us to understand the degeneracy breaking that occurs at the high symmetry points. We discussed the gamma point yesterday, and we started the discussion about the x point. So in the previous lecture, last time we discussed the lowest energy state at the x point. This in the empty lattice approximation. This is a double degenerate state, and the degeneracy is broken into two non-degenerate level of symmetries, x1 plus and x4 minus. So this was the discussion we had last time. Just to go back to our original description, again, if we consider only kinetic energy, the bands are written as the kinetic energy of different plane waves with wave vector k minus g, and g is a reciprocal lattice vector. And so the g vectors for a cubic lattice are simply that, where n1, n2, and 3 are integers. And since we are dealing here with the x point, so the x point for the simple cubic lattice is simply pi over a 1, 0, 0, right? So in this case, then the expression for all possible energy states at the x point is given by h squared 2 over 2m 2 pi over a square, and here 1 minus and 1/2 minus n1 square plus n2 square plus n3 square. Okay, so this is the general solution. And then the first energy level, this one that we considered last time, is obtained by the lowest energy solution in this case, which is n2 equals to n3 equals to 0, and then n1 either equals to 0 or 1, right? So I have two solutions with the same energy, and n1 equals to 0 or plus 1, right? And in both of these cases give me this energy level, right? h bar square over 2m 2 pi over a square times 1/4. So, and then this is the case we discussed last time, and this degeneracy is broken and into two non-degenerate states. So now today we are going to start discussing so just forget about this. We are going to start discussing okay, so sorry, going back to the discussion we had last time. We also found out what are the properly symmetrized combination of plane waves in this case, there is a symmetric and an anti-symmetric combination. One is even under inversion. It gives me a cosine here, and the other one is odd under inversion. It's a sine function. This one is x1 plus, this one is x4 minus. Okay, so this was the end of last lecture. And what we're going to consider today is let's discuss the degeneracies and how they are split here at the second energy level, at the x point, okay? All right. So now for the second lowest energy level, if we go back to this general expression, let me write that again. The general expression at the x point is this. And for the second lowest energy level, we have different cases to consider. So I think it's easy to see that E2 is obtained when we choose either N2 or N3 equals to 0, and the other one equals to plus or minus 1. That is, I have this case, N2 equals 0, and N3 equals to plus or minus 1. Two different possibilities. But I can also have or N3 equals 0 and N2 equals to plus or minus 1, right? And regardless of these four choices, I must combine that also with the two possibilities for N1. N1 is either equal to 0 or equals to 1 plus 1, okay? So that gives me eight plane waves. That is 8 different g vectors that corresponding to 8 different plane waves, which have the same energy initially in the empty lattice approximation at the x point. And the energy is this, precisely this particular value of E2. Okay, so one can write explicitly what these g values are in this notation, N1, N2, and 3, and these are going to be equal to 0, plus or minus 1, 0, 0, 0, plus or minus 1. These are 4 states, and the other 4 are 1, plus or minus 1, 0, and 1, 0, plus or minus 1. Okay. So this picture shows us how these different g points, these different points in the reciprocal lattice, where they are located in space. So all right, so let's see if this is clear. This is the origin. This is kx, the x coordinate in reciprocal space, ky and kz. So this is the origin. This is the x point, which is pi over a along x, and there is a reciprocal lattice vector here. But the 8 reciprocal lattices we are interested in are these guys. I'm going to color them with red ink. So the 8 vectors we are interested in are these ones. these correspond to, they are located in this kx equals 0 plane, right? In dashed line here, this is the kx equals 0 plane, and these are these 4 vectors here, and the other 4 vectors I'm gonna draw with empty symbols, and they correspond to these guys here. So 2 pi over a, the x coordinate, and the y and z coordinates are those ones. Okay, so you can see that all these 8 different points, they are equidistant from the x point, and that's precisely the condition that we must have, right? Because I mean the energy, remember that we are dealing with different parabolas, all of them centered at these g vectors. So the distance in k-space between these points and the x point must be equal, so that the kinetic energy of all these plane waves are the same at the x point. Okay? All right. So very good. And if we can actually write the plane waves explicitly. Again, the plane waves are psi, well, not psi k, but I mean these are the plane waves basis functions, which in this case, so the e to the k minus g dot r, right, for these 8 different cases, and k is the x point, and these are the different plane waves that one gets. Okay, 8 different functions. These will be basis functions to expand the wave function in the vicinity of that particular energy level. All right, so the next step, as we did last time, is to obtain the equivalence representation. So the equivalence character, the characters for the equivalence representations for this set of 8 plane waves are obtained by considering how many plane waves remain invariant when I apply all the different symmetry operations of the group. So, and in this case, we are dealing with a D4H group, because this is the group of the wave vector at the x point. And in this case, it's quite simple, because, okay, the identity, for the identity representation, the 8 reciprocal lattice points remain invariant, but for almost all of the other symmetry operations, all these points move around. Okay, so they do not remain invariant. So you can go ahead and check that. But for instance, C2 is a pi rotation about the kx axis, and you can see that it shuffles all the reciprocal lattice vector. So the character is 0 here. The same for C4. The same for C2 prime. They will almost all of them are going to be equal, except for this one, the C2 prime axis. What is the C2 prime? A rotation combined with inversion. The C2 prime, it's a rotation with respect to the one of the perpendicular axes, either the y-axis or the z-axis. Okay, about the x point. So you can see that in this case, if you combine that with inversion, some of these plane waves, 4 of them actually, for this particular C2 prime rotation, you see that this guy under C2 prime goes right here, and after you apply inversion it goes back here, right? And the same for these guys. So these four guys, these four reciprocal lattice points are invariant, and that therefore the character 4 here. All right, so this is basically repeating what we did last time, but it's a more complicated, slightly more complicated case because we have more plane waves to consider, but essentially it's the same thing we did last time. And then the next step would be then to decompose that into irreducible representations of the group of the wave vector. I'm not going to do this exercise, but this is the result. This is the final result then for the decomposition. And x1 plus x2 plus are non-degenerate states. x5 minus is a double degenerate state. x4 minus x3 minus are odd under inversion non-degenerate states, and x5 plus, so the degeneracies here are 1 1 2 1 1 2, and the pluses and minus signs refer to even or odd under inversion. Okay, and again one can do the same exercise we did last time, but again slightly more complicated, to find the properly symmetrized combinations of plane waves that transform according to all these different representations of the group of the wave vector at the x point. I'm not going to do that, but this is the result that one would get. These for the 1D representations, and these is the two partners for each of the 2D representations. Okay? So, going back to our original band structure plot using the empty lattice approximation, this set of 8 plane waves here with the same energy, when you apply the crystal field, the crystalline potential, it breaks into 2 double degenerate states and 4 non-degenerate states. Okay, very good. So this is the end of this discussion on the X point, and I think I have shown you this a similar picture in last time. This is to compare the band structure of BCC sodium in the empty lattice approximation. These are the upper plots. So these are the empty lattice approximation, and you see all these degeneracies here. And here, in this case now, we show plots showing the real calculations, in which one sees that how the degeneracies are broken according to the different symmetries, different high symmetry points and high symmetry lines in the Brillouin zone. And this is just to emphasize the similarity between the empty lattice and the full calculation, except of course for the fact that the symmetry breakings given by the effect of the crystal potential. Okay? All right. So let's move on now. This is the final section of this chapter, and we are going now to consider the effect of glide planes and screw axes. That means the effects of Nonce morphic space groups, and as we are going to see, this has some interesting effects on the degeneracy of band structures in certain high symmetry points, as we are going to see, because of effects related to the existence of these glide planes and screw axis symmetry operations, we are going to see here that in some cases that leads to the bands sticking together. This is an expression that people use in this field, bands stick together. That simply means that they are degenerate because of that particular kind of symmetry. And first we are going to see how this happens in a very simple case, that is a 2D space group. This is the simplest space group with a glide plane. This 2D space group number 4, and it's a rectangular lattice. Let me call this the x and this the y directions. This is not a uniform notation, but let me choose that for a minute. And these are, we can imagine that these are, let's suppose these are atoms, right? The same kind of atom, same atomic species. And you can clearly see there are glide planes, right? There are glide planes. There's a symmetry operation in which you reflect by this plane, combining with a translation by half of the unit cell along this direction. Okay, this is the simplest possible case of a glide plane. Okay, and let's try to see what is the effect of that symmetry on the band structure, specifically the band structure at the x point in the Brillouin zone, at the boundary of the Brillouin zone. But we are going to see that actually the same happens for all these points here along this line. But let's consider first the case of the x point in the Brillouin zone. Okay, so before we analyze this non-symorphic group, let's take a step back and see what happens for a symorphic group. And in this case is a 2D space group number 3. Then in this case we don't have glide planes, it's just a simple rectangular lattice. And let's see what happens. So we are interested in the solutions at the x point. And if you think about it, the lowest energy solutions at the x point, they are going to be very similar to the ones we considered for the cubic lattice. Because, I mean, the rectangular and cubic, after all, they are not very different if you consider only the physics along one direction. So it's very reasonable to expect that one could guess that this is, if you consider only the plane wave part, right, of the Bloch function, this is the sum of two of the two plane waves, one at the gamma point, one at 2 pi over a, which gives me the cosine. Let me call this psi plus, and the odd under inversion solution gives me a sine, and let me call this psi minus. Okay, so let's assume this is a given. This is given to us. It's not implausible, and what I want to show you is that this will certainly, these two solutions will certainly give me, in this particular case, different energies, right? And after that, I'm going to show you that for this particular case, this is going to give me the same energy, so they should stick together. They should be degenerate in this case. Okay, so let me start by drawing. So I will try to adapt this plot here, and let me draw here the two wave functions as a function of x. So this is 0, this is a, the lattice constant along x, and one is a cosine and the other is a sine. But remember, is a cosine of pi over a, so the wave function switch sign, right? Because I'm talking about the x point, so it should switch sign when I travel by a lattice constant a along x. And let me use another color. Let me draw now this is the even under inversion solution, and let me draw the odd solution, which is a sine function. So the sine should give me something like that, right? So one is a sine, the other is a cosine. Okay. All right. So now let me calculate the energies, right? So the energies, as you can expect, they are going to be well, there's the kinetic energy, which is basically the same for both of them because they too oscillate with the same frequency, right? So the same wavelength. But what is important to consider here is the potential energy. And for the potential energy, actually what is more relevant to draw here is not the wave function, but rather the psi square, the wave function square, which gives me the probability of finding the electron. So if I draw psi square here, the probability of finding the electron along x, and you see here that for the cosine solution should give me something like that, right? So again, this is my x direction. And for the sine solution, it should give me something like that, 0 here, and with a peak here right in the middle, and 0 here. Okay? So this is cosine square and this is sine square, basically. All right, so okay, so what about the potential energy? So let me suppose that these little balls are atoms, atomic nuclei, so they have an attractive potential with respect to the electrons. So the electrons like to be near the nuclei, right? So I could then go ahead and draw the potential energy. Let me draw the potential energy. It's a function, let me call it u, as a function of the position x. And as I said, this should be small here, up to a constant. I don't care too much about the constant, but should be small here, near the near this plane where we have ions or nuclei, and should be higher here, and then it should be small here again. The exact form, functional form of that function, we don't know. It could be very complicated, but you see that it oscillates, and it oscillates with a very specific, well, at least the lowest frequency, right? The lowest harmonic of this is a cosine, a function of cosine of 2 pi over ax, right? So it's a reasonable assumption to say that u of x, you see that the y coordinate is irrelevant for us, but it's like something like negative of a cosine function, right? cosine. It actually looks like a sine of 2 pi over a too, and something like that, up to a constant, right? So it could be a sine function as well. So plus some function of multiplied by some function of y that it's not very important in this case, up to a constant. Okay. So minus cosine and sine up to a constant are basically the same function. So so what's the idea? The idea is that I can now try to calculate the expectation value of the energy for the cosine solution, and you can see that I have a cosine square of pi over a that essentially up to a constant is a cosine of 2 pi over a, right? So this is gonna give me some number you can integrate between 0 and a, and the cosine square 2 pi over ax, and this is going to give me some number minus v0 over 2, and again the y coordinate is completely irrelevant in this problem. So but now when I calculate the energy for the odd solution, this basically is going to be proportional to the integral of, now I'll have sine 2 pi x over a times the cosine 2 pi x over a, and this is going to be 0. So clearly the even solution has lower energy than the odd solution, and we could actually guess that even without having to do these calculations, is just look at this and see that you can see that the odd solution, so the red function here, which is the even solution, has a larger probability of finding the electron in the plane in which we have atoms, right? So that lowers the energy of the electron, and the odd solution with the sine function has a larger probability of finding the electron in this plane, intermediate plane, in which we don't have atoms, right? So that gives me a higher energy. Okay. Now you can already see where this is leading us when you consider now the Nonce-morphic structure. So if you take now the Nonce-morphic structure, that's the same thing. Let me draw here the once again the sine and let me draw psi square. So psi x square plus, in red, the cosine function, and in blue I can draw the sine square. So in blue, psi minus square. And then I hope you can see that in this case they should have exactly the same energy, right? Because both of these probability distributions, they have peaks at atomic planes in which we have atoms, right? So, and should one could calculate this mathematically, but I mean, if you want to be more explicitly, one could draw the atomic potential. So the difference is now the atomic potential has more oscillates with a larger spatial frequency, right? Because I mean, this is lower energy, and then the energy increases. Sorry. So the energy as a function of distance potential energy should be something like that. It's a dip whenever I have an atomic plane, a plane with atoms. And in this case, I have an extra atomic plane right here in the middle. So in the previous case, I had a potential energy oscillating with a 2 pi over ax. So, and in this case, what I should expect that the potential energy in this case is roughly a cosine of 4 pi over a. Oscillates twice within one unit cell. Okay, so that should be, let's say, the lowest harmonic of this potential energy, right? And then when you calculate, you can do this exercise. When you calculate the expectation value of the energy for both solutions, for the even and for the odd solutions, you're going to see that this is equal. They are equal to each other. Okay, so that means that this energy level at the x point is degenerate. The degeneracy is not broken by the effect of this particular form of the crystal potential, and you see that this is a direct consequence that I have an extra atomic plane right here in the middle of the unit cell. So it's a consequence of the glide plane, okay, operation. So in this case, there is a degeneracy, and the bands then stick together at the x point. So there's another way to understand that, as we discussed last time, which is, if you remember, the description of the band structure in terms of the nearly free electron model. So in our particular case, this should be the gamma point. This should be 2 pi over a. This should be the x, kx. And this is the x point, right? And you see that these are the two parabolas coming from the two reciprocal lattice vectors. They cross here. And I have said last time that the size of this gap is proportional to, or is twice the absolute value of this particular coefficient in the Fourier expansion of the crystal potential. So in our case then, this should be u of g, in which g is equal to 2 pi over a x, right? So another way to interpret this result is that whenever this is 0, and in some cases this is 0, but whenever this is 0, there is no gap opening. So the bands simply cross. They will just cross here. And there is this degeneracy, the bands sticking together here, which is this degeneracy is not broken. And this is precisely what we see here, because you see that in the previous case, okay, there is some Fourier component of the crystal potential oscillating with a 2 pi over a wave vector. But for this Nonce morphic structure, there is no such Fourier component. The lowest Fourier component is 4 pi over a, right? So in this case, precisely, this is 0, and that's another way to see why this degeneracy is not broken in this case. There's a third way to understand that, which is based on the structure factor. So what is the structure factor? Well, there's an expression for U of G, the Fourier component of the crystal potential. I'm not deriving this, but you can see this in basic solid state books, which is, this can be written as one of the volume of the unit cell, a sum over all atoms in the unit cell, and this term tau j is the position of the atom j. This is called this is some interference factor times some function which is called the form factor or atomic form factor. So this comes from the atom, right? So this is essentially the Fourier transform of the atomic potential. So, and then if I have two atoms, two equivalent or two atoms of the same species, two atoms of the same kind, of the same type in a unit cell, then phi 1 is equal to phi 2, and then I can remove that from the summation. So the structure factor or the Fourier transform of the crystal potential is simply phi and this interference factor, which is sometimes called the structure factor. J equals 1 or 2, and e to the minus I j dot tau j, g dot tau j. So one can see from this expression there is that in some cases, whenever this interference factor, which is again sometimes called the structure factor, whenever this vanishes, whenever this is equal to 0, then we have this effect. I mean, the two bands are going to stick together here and at this point, and the degeneracy is not going to be broken. Okay? So the book calls this structure factor. Even though the term structure factor has a different meaning in X-ray crystallography, but these are very similar concepts. So what happens in our case, in this particular case that we are considering here? In our case, we have two atoms. Let's say one it's at the origin along X, and there's some small displacement which is irrelevant in Y, and the other one, this is atom number 1, this is atom number 2, and the other atom is at a over 2 along x and plus delta along y, right? So for g equals to 2 pi over ax, which is the g we need to consider in this case, let's calculate the structure factor. So the structure factor is going to be the sum over j e to the minus I j dot tau g dot tau j, and this is 1 for this guy, plus e to the minus I pi for this other guy, and that gives me 0. So there's another way then to show you why these two bands stick together because of this glide plane. All right? Excellent. So let's see what happens in more complicated structures, for instance, in 3 dimensions. There is some important cases in 3 dimensions, very well-known cases, in which the same effect happens. One of them is in the Hcp structure. This is the Hcp structure, the hexagonal closed pact. It's a hexagonal lattice here, and it's not a Brovell lattice. The Brovell lattice is hexagonal, but you have 2 atoms per unit cell. One atom here in this plane, and the other one at this middle plane here. Okay? So there is a it's a non-symmetric structure because some of the symmetry operations will require a translation by this vector that goes from the origin here to the middle of the unit cell, and this is a non-symmetric structure. So in this case, bands will stick together at the so-called A point in the Brillouin zone. So this is the first Brillouin zone of the Hcp structure. This is the gamma point, and the A point is right in the middle of the of this hexagonal face. The A point is along Kz, right? It's 2 pi over C 001. C is this lattice constant here. So in some way, there's an analogy between this case and the case we have considered before. Okay. So, and this is the character table for the point group C3V for the group of the wave vector of the point A in this particular structure, and you can see right away that all irreducible representations there's not a single degenerate. There's not a 1D representation. All representations, they have dimensionality 2 or 4. Okay, so all states at the A point, they should have at least a double degenerate or sometimes a 4-fold degenerate level. And this is a calculation of the band structure of titanium. Titanium is a metal that crystallizes in the Hcp structure. And you can see exactly that. At the A point, you see the bands seem to stick together. They are always, there is always some sort of degeneracy at these particular point in the Brillouin zone. And that's a result of this non-symmetric space group. And the other very famous example is the diamond structure. The diamond structure, as we have seen, is a non-symmetric structure because some of the symmetry operations require translation by tau d, where tau d is a over 4, 1, 1, 1, right? And this will give rise to degeneracy, bands sticking together at the x point. So let's calculate the structure factor in this case at the x point. Now be careful, because for the FCC lattice, and the diamond structure has an FCC Brevet lattice, the x point is not pi over a 100, but is 2 pi over a 100. And therefore the g vector that we want to, so this is gamma, this is a x point, and the reciprocal lattice vector g that it's important to consider when evaluating the structure factor here at the x point is 4 pi over a 100. So if you calculate now the structure factor, sum of the two atoms in the unit cell, e to the minus I j dot g dot tau j. So the two atoms are one at the origin, right? Tau 1 equals to 0, 0, 0. And the other atom is located at tau d. So, and then I have here 1, and the dot product between g and tau d, which is again pi, minus I pi here, and this is 0. So again, in this case, the structure factor vanishes, so we expect bands to stick together at the x point for the diamond structure. All right. So, and then there's another interesting thing which is related to the derivative or the slope of these bands at the x point. There is a deeper explanation about that in our textbook. I'm not going to go through that at this moment here in the course, but if you see here in this simple picture, you can see that if this degeneracy is not split, you see that these bands, they basically cross each other, right? It's almost like they don't care about each other, they don't see each other, they don't interact, right? And so it's like there's a continuation of both bands in terms of the orbital character, for instance, or the symmetry of one state with respect to the other. And this is band crossing, don't change the slope. But sometimes there's this, well, when the potential, the Fourier component of the potential is non-zero, then there is the anti-crossing, and then the slope is 0. Okay. The situation at the x point is slightly more complicated, because you can see that for some symmetries, for x1 and also x2, you see that the slope is non-zero, but for x3 and x4, the slope is 0. And this distinction is explained in our textbook. But this is the character table for the x point of the group of the wave vector. And you see again the x1, x2, x3, x4 irreducible representations. They are both two-dimensional. All of them are two-dimensional irreducible representations, meaning that all states here at the x point are doubly degenerate. Okay, for the diamond structure. And this is an important case that we are going to explore that slightly further in a couple of chapters from now, when we discuss the effects of spin, and we are going to see how spin orbit coupling will change this picture that we are considering. So this plot is the band structure of germanium. This is germanium band structure without considering spin orbit effects, and we are going to see that spin orbit changes this picture slightly in some important ways in a few particular high symmetry points in the Brillouin zone. All right. Okay, so this is the end of chapter 12, and there are 2 problems due next Wednesday, and thank you for your attention.